You click a website, and in milliseconds, your data travels through an entire network you never see. So what actually happens to that packet? Let's follow it step by step. The packet starts on a client AS, an Ethernet frame carrying an IP packet. This initial structure defines its starting point and ultimate destination. At the router, the Ethernet header is removed and replaced for the next hop. While the layer 2 information changes, the core IP packet remains completely unchanged. The packet enters the day-do center, where leaf switches connect devices and spine switches transport traffic across the high-speed fabric. At the leaf switch, traffic is segmented using virtual LANs, or VLANs. Each VLAN acts as its own isolated layer 2 network. Devices in different VLANs cannot directly communicate. Traffic must pass through a router to move between these independent domains. To extend these VLANs across multiple physical switches, networks use trunk links. Each frame is tagged with a VLAN ID using the IEEE 802.1 standard to maintain its identity across the wire. But there's a catch. VLANs use a 12-bit identifier, which means they can only support 4094 usable networks. In a modern hyperscale cloud, that becomes a major limitation. Modern networks separate into two layers. The underlay is the physical IP network. The overlay carries the original traffic. VXLAN allows legacy layer 2 traffic to travel seamlessly across a modern layer 3 IP network by using a technique called encapsulation. By moving from a 12-bit to a 24-bit identifier, or VNI, VXLAN expands the network capacity from 4,000 to over 16 million unique segments. This wrapping and unwrapping happens at a VXLAN Tunnel Endpoint, VTEP. A VTEP is simply the device, like a switch or hypervisor, that converts a normal Ethernet frame into a VXLAN packet and back again. The VTEP wraps the original Ethernet frame, including its VLAN tag and IP packet, without modifying it. First, a VXLAN header is added containing flags and the VNI. Next, a UDP header is added with destination port 4789. Finally, an outer IP header is added to carry it across the network. Across the network, devices only look at the outer IP header. The inner packet remains untouched and invisible. But how does the network know where to send each packet? This is handled by Ethernet Virtual Private Network, EVPN. EVPN acts as the control plane. It shares MAC and IP information between VTEPs, so traffic is sent directly to the right destination without unnecessary flooding. Keep in mind, encapsulation adds about 50 bytes of overhead. If your network MTU isn't configured to handle these larger packets, they will hit a barrier and be dropped. Once it reaches the destination VTEP, the outer layers are removed, revealing the original pristine Ethernet frame to the receiving application. The restored Ethernet frame is forwarded to the destination device. Because the original Layer 2 and Layer 3 information was preserved, the host processes it just like any normal packet. So when traffic enters a modern data center, it's separated using VLANs, scaled using VXLAN, encapsulated at VTEPs, and intelligently forwarded using EVPN. If you're curious about how these complex systems work behind the scenes, subscribe at What Really Happens. We break it down step by step.